Hello, I'm Michael from Team 14343 Escape Velocity, and today we'll be doing a presentation series on squid control. So here's an overview of the topics we're going to be covering today. We'll go through standard PID controllers, why they're not suitable for FTC, why SquID is a better alternative, and then we'll go through some proofs of how and why SquID works. We'll do some empirical comparisons, and then we'll talk about ways you can make SquID even better. So let's start with a brief introduction to PID control. So let's say you wanted to move a linear slide to a certain extension, like maybe you have slides that you want to move to the high basket for in 2024 into the deep. So how would you do this? One way you could do this is with what's called a P or a proportional controller. So we can use the built-in motor encoder to measure how far the motor is from where it needs to be, and then we can multiply that distance by a constant, and that'll basically, if it's really far away, it'll go super fast, and then when it's really close, it'll slow down and be able to stop exactly where it needs to. So this is a working solution, but the problem is what you end up with is a lot of oscillations. So the slides will move up, and then they'll move a little bit too far up, and then they'll move back down, and they'll move a little bit too far down, and it'll just bounce around right around where the slides need to be. So a slightly better solution is what's called a PID controller, or a proportional integral derivative, and this is pretty standard for FTC. Actually, the integral term isn't used as much, so sometimes it's referred to as a PD controller or simply proportional derivative. But this is very standard for FTC because what the derivative term allows us to do is it allows us to factor in how fast our mechanism is currently going. So in the case of linear slides, the faster the linear if the linear slides are moving really fast, we can increase the dampening term or the derivative term in order to slow them down. So this prevents a lot of the oscillation that we see with the P controller. And because we have more constants, we're able to get more constants to do different things, we're able to get better results. However, there are still a lot of problems with PID, especially when you run. So initially, we wanted to use PID to move our robot around. So we would run a PID on our robot position, and then we would use that to move our robot around. But what we found was that we actually had a lot of trouble making a single PID that would do everything we wanted to. So when you tune a PID, you usually play around with the values for the proportional constants for like P, I, and D, and then you do test movements. So you just move the in our case it was a robot. You send the robot to some point, you send the robot to a different point, and you see how well it works, whether it's reaching the position, how much it's oscillating and overshooting, stuff like that. And so what we found was when we used a large distance between the points we were using when tuning, so when we were doing large movements, then the robot didn't have enough power to reach the small movements well. So when we asked it to move 5 inches, it would only move like 3 inches, and then it would stop. And this would actually break our entire autonomous because at the time we had a poor solution for figuring out when the robot could get to the point. But even if this didn't break our entire autonomous, like obviously you want to be able to move 5 inches when you tell your robot to move 5 inches. And we actually found a similar problem for when we use small distances in between points when tuning. The robot would move 5 inches when we told it to move 5 inches, but then when we tell it to move 30 inches, it'll move 40 inches, and then it'll overshoot by a ton, and then it'll have to correct the other way, and it'll be really slow, and sometimes it'll just run into things because it's overshooting so much. So there are a few mitigations for this. One of the most common is to use 2 different PID controllers, one for very far distances and one for smaller distances, and this generally works pretty well, but this doesn't really address the fundamental issue. And what it's really doing is it's kind of just being a simulated copy of what we'll get into our next, which is our SquID controller. So we developed our SquID controller to solve many of the issues we had with the PID controller. So SquID is fast. It's just as fast, if not faster than PID. It's very precise, more precise than PID is, even with PID being tuned for the right distances. It's really easy to tune. There's only one thing to tune instead of two things with a PD controller, and it's really easy to understand. It doesn't actually require calculus like PID does um, to understand how it works. And most importantly, it solves the initial problem that we had with PID, which was that it just wasn't working for small distances and large distances. So you only need one SquID controller. It will do both of them at the same time very well. So how does SquID actually work? SquID follows what's called a control law, which basically tells us how our system is going to respond when. So it basically tells us how our system is going to try to reach a point. So with PID, we have the response is equal to the proportional sum. So again, going back to our linear slide example, we'll have the distance to the basket, and we multiply that by some constant. And then we also have an integral term, and this integral term accumulates over time. So it takes into account like every past error and also the current error, and that's useful for like reaching the target more accurately, because if you're really close to the target but the proportional term isn't strong enough, then the integral term will eventually boost it over. And then we also have this derivative term, which allows us to compensate for the current velocity of the mechanism. As we mentioned earlier, if the slides are going too fast, the derivative term will slow it down. So it's a relatively simple equation. It's not super hard to understand. All the terms are basically just constant multipliers. SquID is even simpler. If we look at the SquID equation, the response that it's going to try to do is just a constant times the square root of the error. And at first, you might be like, that doesn't make any sense. Why would we want to multiply the square root of the error? And we will get to that. But first, let's talk about some important caveats for SquID. So the first major caveat is generality. So PID is a very general controller. It's used a lot in a ton of different places, not just FTC. And SquID only works for very specific things, even within FTC. So PID, I have a little table here. PID can regulate the temperature in a building. It can control the speed of a motor. It can help stabilize an airplane. It can basically anything like any system where you can like modify a variable. PID will probably work pretty well on it. SquID doesn't really do that. SquID can control the position of stuff. You can control the position of a motor. You can control the position of a robot. You can control the position of an arm. You can control the position of linear slides. Especially in FTC, a lot of what you're going to be using SquID on is mechanisms that are run by motors. So linear slides, a drivetrain, an arm, all that kind of stuff will work. But like you wouldn't want to use it to regulate the temperature in your house. And this actually gives us a little bit of insight into why SquID is able to beat PID, because PID is such a general controller that it can't be excellent at any one thing. It has to be decent at everything. And SquID instead is targeted. It prioritizes this one action, and that's what makes it able to perform better than PID. Another important caveat is the square root. So if we look back to the control law for SquID, we'll see that there's this pesky square root in this equation. So as you probably know, the number inside the square root needs to be positive, but it's possible our error is negative. Like if we're trying to travel down our linear slides, so if we're at the bucket position and we're trying to retract our slides, the error will usually be negative, and this would cause an error with our code. So instead, what we need to do is we need to square root the magnitude of the error, and then we need to multiply it by which direction the error was originally in. I have pseudocode and also Java code at the bottom of this slide that basically demonstrates how you do that, but we want to take the absolute value of the error, we square root that, and then we multiply it by what the sign of the error was. And now we're going to get into why SquID works really. So one way we can prove the effectiveness of SquID is we can basically take the physical equations that model our robot or our arm or any other mechanism that we're powering with a motor, and we can basically find the SquID control equation hidden in those equations. So let's start with some definitions. D is our error. It's how far away we are from the target. A is our maximum deceleration. It's if you think about the brakes in a car, it's how fast your car can stop once you're pressing the brakes. VI is our target. It's our target current velocity, so it's how fast we want to be going at the instant in time that we're running the SquID. And VF is our final velocity. It's how fast we want to be going once we reach our target. So the first thing we can do is conclude that our final velocity should be 0, because once we're at the place that we want to be at, we generally don't want to be moving anymore. So our final velocity can be 0. And then we can use a little bit of physics. So distance is equal to rate times time. So the next equation, d equals vi plus vf times t over 2. That comes from this distance equals rate times time idea. So obviously we have t for time and d for distance. And the rate is the average rate that we're going to be going at, because if we have our initial velocity that we are at right now and then our final velocity, our average speed is just going to be like the average of those. So we add them up and we divide it by 2, and that's how we get that equation. And if we rearrange that equation a little bit and we also put in that the final velocity should be 0, then we'll get that time is equal to 2 times the distance divided by the target initial velocity. And the other thing we can find is that the target initial velocity should be the maximum deceleration times time. And this is because we always want to be decelerating as fast as possible. Like we want to go as fast as possible, and then we want to slow down as fast as possible. So the fastest possible way to slow down would be to use the maximum deceleration. So that's why we get this maximum deceleration times time, because it's going to take t time to reach the destination, and then in that time we're going to be able to decelerate by the maximum deceleration times time. And if we substitute the equation from time that we got earlier into that equation, and then we rearrange a little bit, what we'll actually end up with is our target current velocity should really just be some proportional term times the square root of d. And if you'll recall, d was our error. So actually, this equation is exactly the same as the control law for SquID, and this is the fundamental reason why SquID works. Another way we can find SquID is through a motion profile. So trapezoidal motion profiles, if you don't know, are a commonly used way to move around mechanisms in FTC, and they basically allow you to like move your mechanisms around with respect to this with this equation that tells you what the velocity of something should be at any given point. And this should already seem very, very familiar. And there's these constants that you can tune that allow the mechanism to basically follow this predefined target velocities and reach the target even better than PID can. So we can compare SquID to the motion profile. So we start with this straight line, because SquID models constantly decelerating at max deceleration because we're trying to slow down as fast as possible. So that would look like this straight downward sloped line, because we're going to start as fast as we can while still being able to stop in time, and then we're just going to slow down as fast as we can. But of course, in the real world, motors, like, you can't give a motor infinite power. At some point, it can't go any faster. So there's going to be some upper limit to what our velocity can actually be, and that's why we have this straight plateau and then this deceleration in this image. And finally, our motors can't get up to speed instantly. Think about the accelerometer in the accelerator in a car. When you press down the gas pedal, the car doesn't just instantly start moving at 60 miles per hour. That's why the 0 to 60 metric exists. So it has to spend some time speeding up first, and that's what this initial slope upwards in the top graph is. And this creates a very familiar shape. This is actually exactly the same as a trapezoidal motion profile. If we look on the bottom, there's a reference image. It's the orange line in the image, but that's a reference image of a trapezoidal motion profile courtesy of Control Alt FTC. And they are actually exactly the same. So SquID is actually basically just a motion profile. And now you might be wondering, why should I use SquID instead of a motion profile? And there's actually a lot of reasons. So because SquID operates on the current air. So usually with a motion profile, we we generate the motion profile in its entirety, and then we just follow the velocity based on time. And SquID doesn't do that because it takes into account how far we currently are away. So if something gets stuck, like maybe the slides get caught on something, the motion profile it won't know how to deal with that properly. You'd have to make another motion profile for that. But for SquID, you can just keep doing exactly the same thing, and it'll work perfectly. It's also easier to implement because motion profiles you have to tune a bunch of constants. You have to add some specific classes and stuff to your code to make it work properly. And SquID doesn't really have that. It basically works like a PID controller, except it has a slightly different control law. And of course, as I mentioned earlier, motion profiles have a lot of constants. SquID does not have that many constants, and also the constants are easier to tune. The only downside of SquID is that motion profiles follow this thing called time consistency, which means that the amount of time taken by an action is generally consistent. And SquID doesn't really follow this because it doesn't use the time-based system that motion profiles do. But but because it doesn't focus on the time as much, it's able to because SquID isn't doesn't focus on the time as much, it's able to be more resistant to those disturbances and better compensate for that. And above you can see a Desmos link to all three graphs in the previous slides. And this slide deck will also be linked at the end of the presentation.